Good day, students. It's class time, your daily space for CSEC and CAPE students. Watch lessons in real time on the Television Jamaica YouTube channel or One Spot Media. We're also live on Music 99 and GoJamaica.com. If you have questions on today's subjects, you can send them to the Television Jamaica's Facebook page at Television Jamaica or Instagram at television_Jamaica using the hashtag TVJClassTime. I am Dr. Francine Taylor Campbell, and I'll be guiding you through CSEC chemistry. In today's session, you will be able to explain how evidence supports the particulate theory of matter, distinguish among the three states of matter, and explain the changes between the three states of matter in terms of energy and arrangement of particles. So let's get into it. We'll start with a few guiding questions. What is matter? How do we know that matter exists? And how do the states of matter differ? Of course, you will remember that matter is found all around us. It has mass and occupies space. Now, mass refers to the amount of matter in a particular material or substance, and the space that it occupies is referred to as the volume. So, it is easy to show that solid substances has mass and occupies space. So let's see. If I have a container, I could easily determine the mass by placing it on a balance, and we would get a value for the mass in kilograms or in grams. Likewise, this container occupies a particular space, and so we can determine its volume. For liquids, we can also determine the volume of a liquid. So we have a measuring cylinder, and I can pour out this liquid into the cylinder and hence determine its volume. And of course, we could also determine the mass by weighing it on a balance or scale. But what about air? Does air have mass? If we were to take a balloon, we could blow into this balloon, need some strength here, and we could easily determine the volume because, of course, we can see that the air occupied some space in the balloon. So air has volume, that is, it occupies space. But what about mass? How could I determine that air has mass? How could we prove that? So here we have a simple demonstration of how we could prove that air has mass. What we would need to do is to get two balloons. Of course, they would have to be the same type of balloon, same size. Place them at opposite ends of a balance, a beam or a piece of stick or a ruler, of course, and place it probably across on a flat surface, all right? And you would, of course, blow up the balloons. Now, if at some point you should take a pin and just stick one of the balloons, you will realize that the beam, well, I shouldn't say, I should ask you, what do you think would happen? We would notice that the beam, after a while, would become unbalanced. Why is that so? That has happened because the balloon, having a greater mass, will tilt the beam in the opposite direction. So, of course, that would prove that air not only has volume, but it also has mass. How do we know that matter exists? If we were to take a block or a cube of sugar or any material, and we were to repeatedly divide this material, after a while, we would reach a point where the material can no longer be divided any further. What would we find at this point? We would observe that there is that point of that smallest division, that would really be a particle. All right? And so we're going to prove this theory. How do we prove this? So if I were to take some water, again, place it in a beaker, and here we're adding some crystals of potassium permanganate. Now, of course, at home, you may not have potassium permanganate, but just in case you have a drink mix, one of those popular drink mixes, you can add it as well. So if I were to add crystals of potassium permanganate, what do you think we would observe? And if we were to leave this over a period of time, what do you think would happen? Or let me add a few more, just to speed up this one. So if we were to observe over time, we would actually see that after a while, the crystals would spread throughout the solution. The crystals would spread throughout the water in the beaker, and this is happening by a particular process. What is that process called? That process is called diffusion. All right, now suppose we were to add same crystals of potassium permanganate or drink mix at home to hot water. What do you think would happen? So we can see that the same process is occurring, but is there a difference? Here, you'll notice that the particles in this hot water, they are spreading a little bit more than those in the cold water, all right? And what that proves is that in the hot water, the particles have more energy, and so they can move and spread at a faster rate. And of course, this proves that matter exists as particles. So this is an example of diffusion occurring where solid particles are dispersed or are moving about in the liquid. So then how could we define diffusion? In this case, diffusion would be defined as the movement of particles from an area of high concentration to an area of low concentration until it has evenly mixed throughout, all right? And if we should leave this over time, we will see what will happen. How else could we prove that matter exists as particles? Consider a gas jar, and we would place two gas jars together and place some bromine gas into one of the jars. Again, if we left it over time, we would see that the gas would fill both jars. Again, why did this happen? The particles in the gas would have spread to fill both jars, and so the particles would have spread through the process of diffusion. Now, how is this concept applicable to us in everyday life? Why do I need to know this? How does it help me? How can I see this happening around me? All right, so consider at home you're using your perfume, or you're spraying out those mosquitoes that are coming up around the place, right? And you spray in one room. What happens to that spray? What do you observe over time? The spray or the perfume would eventually spread throughout the entire house. And it is able to do that because the particles in the spray are moving from an area of high concentration in one room to an area of low concentration until it is spread throughout. That is, again, an example of diffusion. Can you think of another example? One that is relevant to you? Okay, let's see. What about what happens when the Riverton landfill is set on fire? Now, in most cases, persons living in the hills of St. Andrew or other places, even in St. Catherine, can actually be affected by the smoke. So how did the smoke travel to these areas? It traveled because, again, the particles from the smoke are moving from an area of high concentration around the landfill to areas of low concentration, and they're able then to spread by diffusion. Okay. Now we look at one more example of how we can prove that matter exists as particles. If you were to take your potato, Irish potato, or any such fruit or food, and you were to place it in water. So in this example, we're looking at potato slices or potato strips placed in a salt solution. So if we were to place it in a salt solution, after some time, what would you observe? Based on your own experience, what do you think would happen? Yes, so after some time, you will see that the potato strips actually would shrink and become what we call flaccid, which is really saying that the water in the potato strips would have moved out of the strips into the salt solution. Now, this is an example of a special type of diffusion, which is called osmosis. And what has really happened is that the water molecules in the cells of the potato would have moved out of those cells into the salt solution. Again, if you had the potato in regular water, not a salt solution now, we would also see that in this case, the potato strips would become firm or harder, or what we call turgid. Again, because the water molecules would have moved out of the solution into the cells of the potato. And so osmosis would describe the movement of water molecules only, right? From an area of low concentration of solute to an area of high concentration of solute. Okay, so how can we now apply this process of osmosis? How can we see it applicable in our everyday situation? So consider what happens when you put fruits and vegetables in water. After some time, you will see that it swells, again, because the water is able to move through the cells by osmosis. This process is also applicable in meat and food preservation. Think about how your grandparents would have cured their pieces of pork or that sort of thing, right? They would have added salt, and the water in the particular produce, in the meat, would have moved out into the solution. And this is a way to preserve the meat. Now, all of this shows that matter exists as particles. When we come back, we will be looking at, we're going to pause right now and take a break, and when we come back, we'll be looking at the kinetic theory of matter. Stay with us.
Reduce your risk of viral illnesses like the flu and coronavirus. Wash your hands frequently with soap and water. Cover your nose and mouth when coughing with a tissue and dispose of it. Avoid close contact with anyone with a cold or flu-like symptoms. If you become ill, please visit your doctor or the nearest health center and share your travel history. The flu and coronavirus can kill. Let's protect each other. A message from the Ministry of Health and Wellness.
Hi there, I'm Simon Preston from TVJ. Thank you very much for watching our YouTube channel. To see our latest videos and also to see live events, click here. To see our full videos on onespotmedia.com, click here. Thank you very much.
COVID-19 tip. Protect yourself and others from getting sick by washing your hands after coughing or sneezing, when caring for the sick, before, during, and after you prepare food, before eating, after toilet use, when hands are visibly dirty, and after handling animals or animal waste.
Reduce your risk of viral illnesses like the flu and coronavirus. Wash your hands frequently with soap and water. Cover your nose and mouth when coughing with a tissue and dispose of it. Avoid close contact with anyone with a cold or flu-like symptoms. If you become ill, please
Welcome back to CSEC Chemistry. Let's look again at what we did earlier. So earlier, we were proving that matter exists as particles. We would have placed some crystals of potassium permanganate in cold water and in hot water. Now, if you were at home, I was encouraging you to use your drink mixes and try the same experiment. So if we were to look at these two beakers, we would see that at this point, the particles have spread more into the water, all right? And it is now forming that uniform solution that we spoke about. And so this, again, is one way to prove that matter exists as particles. Now, the theory, that particulate nature of theory, or the kinetic theory of matter, has some assumptions. From that theory, we can say definitely matter is made up of tiny particles. The particles are in constant random motion. That means that the particles are not static, they're constantly moving. The best demonstration of this is, of course, when we look at a gas. The gas is constantly moving, and so we can see that the particles are in motion. We'll also see that the particles have space between them. And so if, for instance, if you were to get a container with marbles or some other stones and you were to pack it, you would see that space exists, and we could fill this space with a liquid, with other fine particles like sand, and again we could add more water and we would still have space in that container because the particles of matter have space between them. The particles then, therefore, can exist as atoms, which of course would be the smallest division of matter. They can exist as molecules, and they can exist as ions. And evidence for these, for this particular theory, as we have shown, can be proven by diffusion as well as by osmosis. Now, let's get to our second question, actually, our third question. How do the states of matter differ? How is it that a solid is different from a liquid and those two are different from a gas? How can I show that? Normally, when we're comparing the states of matter, we compare them essentially based on the energy and arrangement of the particles, or the forces of attraction between the particles. And so, let us demonstrate right now what we're talking about. So if I were to show how a solid is arranged, so consider a cube and consider some solid particles packed in this cube. So let me start again. My diagram is a little off. So in a solid, how are the particles arranged? The particles in a solid, and you're going to tell me how they're arranged. So this would be the particles, right? The particles are supposed to be exactly the same, all right? Forgive me, right? So this would be solid. What do you notice about these particles? How are they arranged? So as you can see, the particles are close packed. So we say in a solid, the particles are close packed, all right? And they really do not move, but they vibrate about fixed positions. Now, if they're close packed, do you think they would have high amounts of energy? Since they're close packed, the forces of attraction between the particles is great. That force is increased, and so the particles are not able to move. And generally, we would classify solids as having low kinetic energy compared, of course, to the other states of matter, all right? They have strong attractive forces between the particles, all right? And of course, we mentioned before that they are close packed. Now, this is why when you place a solid on a surface, the solid remains. It has a definite shape and it has a definite volume. So that would explain the arrangement of particles in a solid. Now, what about a liquid? How would this differ from a solid? So if we were to draw some representation of a liquid, again, in this case, I have 8 using the same number of particles. So in a liquid, I'll still have the particles. That's not 8, that's 12. Okay, all right. So in the liquid, you will see that although the particles are close together, we have more spaces between the particles, all right? And so in a liquid, how would that affect their energy? Would they have more energy from than a solid? Definitely, because here they are able to move around more. So they have more kinetic energy than a solid. And the particles are not as close packed, and so the forces of attraction in this particular case, it's balanced with the kinetic energy. So what you'll find is that liquids, the particles can slide past each other, or we say that liquids flow, right? And so the attractive forces, medium between solid and the gas, all right? And so we say that the particles are able to flow and they're not as close packed. Sorry for the terrible writing. All right, now let's consider a gas. How do you think the particles of a gas would be arranged compared to the solid and the liquid? So in a gas, would the particles be close together? What about their energy? Would they have vast amounts of kinetic energy? Yes, that is what would happen. So because the particles in a gas, they have large amounts of kinetic energy, they are constantly moving. Right? So they're constantly moving. They're certainly not close packed at all. They are very far from each other. So the particles far from each other, and they are constantly moving. And this therefore means that they have little attractive forces between the particles. Okay? And so that would essentially explain how these particles, the arrangement and the energy of the particles differ. So of course, in a gas, you see that they're really very far apart, all right? And we normally show a little thing to show how the particles are moving in different directions, all right? Because what you notice is that a gas will always fill any space that it is placed in. And here we would see that solids, liquids, and gas differ based on, again, the arrangement of the particles, the energy of the particles, and the attractive forces between the particles. And these attractive forces will determine physical properties such as melting and boiling points. So for instance, if you can think of water, the boiling point is about 100 degrees Celsius. But if we were to look at a gas, such as carbon dioxide, the boiling point would essentially be in the negative numbers, like negative 78 or some value like that, all right? And so we can definitely see that the attractive forces would determine how quickly these substances can boil, can melt, and will show different properties. Okay. Now, how do we convert from one state of matter to the next? So if I have a solid and I wanted to change it into a liquid or a gas, what would I need to do to convert from one state of matter to the next? Now, when we looked earlier at the arrangement of the states of matter, we were able to show that the energy of the particles basically differ. So it means that if we should apply something that would change the energy of the particles or give it more energy or take away its energy, give it less energy, then that is able to change the substances from one state to the next. And what we normally do in a case like this is to add heat or remove heat. And that would show us how to change from one state to the next. So let's go and demonstrate this in this example. Oops. Now you would be familiar with examples. You're boiling your water, and after some point, the water will change from a liquid to a gas. Or, popular example, you take out your ice from your refrigerator and you leave it outside, and after some time, the solid, the ice, melts. All these are examples of how the matter, the states of matter, can be converted from one to the other. So, we have our solid. How do I convert my solid to a liquid? What is that process called? And if I have a liquid, how do I convert that liquid to a gas? What is that process called? And suppose I wanted to go in the other direction. How could I get from a gas to a liquid? What would I need to do? How can I get from a liquid to a solid? Let's see. So, again, let's use a popular example that you know. So we can use ice. So let's consider ice. Ice is solid water, all right? Good. And if you're at home and you take out that ice, put that ice in your lemonade, we find that the ice, that solid, what's that process that causes it to change from a solid to a liquid? We call that process melting, all right? So we should be familiar with that. We call that melting, all right? What has really happened? Why did this ice melt? What happened to the ice? We would see that essentially the ice freezes, well, ice forms at 0 degrees Celsius, all right? For it to change to a liquid, we would be adding heat. Heat there is a form of energy. So we're adding heat to the solid. So imagine heat added. So when I add heat, I can change from a solid to a liquid. Okay, all right? We're now at the liquid. We have our water. How do I convert that water to a gas? What do I do? Yes, you boil the water and you boil it until it evaporates. And so that process is called evaporation. Again, we're adding heat to change from a liquid to a gas. So, if we added heat to change from solid to liquid, and we added heat to change from liquid to gas, how could I reverse that process? If I had a gas, let's look at a popular example, one that you can relate to. When you're cooking on your stove and you cover your pot, the steam is coming out. When you cover the pot, what happens? What do you notice when you open that cover? You will see that the steam that was forming would start to condense on the surface of that pot cover or that lid, right? And so what has happened is that the gas is becoming a liquid, and which essentially is condensation. So that change from gas to liquid is condensation. What are we doing in terms of heat? Are we adding heat to change from a gas to a liquid? Or are we removing heat? Here we are definitely removing heat. So to move from a gas to a liquid, we are removing heat. Let me see how I can place this. Or essentially we are cooling it. So that is the same thing that happens when you have your cold drink. If you leave your cold drink on the surface for any period of time, you will see that over time there are some droplets forming on the outside of your drink. What has happened there? The water vapor in the air basically has condensed on the surface of your bottle, your cold bottle, all right? And in that condensation, it has changed from a gas to a liquid. Okay, so how do we move from a liquid to a solid? What is that process called? That process is called freezing. And we do it every day when we use the refrigerator, right? Freezing, and in this case, again, we're removing heat or cooling this substance. Now, we could also change directly from a solid to a gas. So, if you had crystals of iodine at home and you were to heat it, you would realize that the solid iodine changed directly to a gas. It did not go through the liquid phase. It went straight to a gas. Can you think of another example? Let's see. For those in theater and those that are involved in food preservation, you would have heard of dry ice. So dry ice is solid carbon dioxide. And when you place dry ice in a particular environment where it starts to melt, it does not go to the liquid stage. It changes directly to a gas. Now, what is that process called, where it changes directly to a gas without going through the liquid phase? That process is called sublimation. So we say then that iodine and dry ice sublimes. Now, this is the same thing that happens when you get those camphor balls. You know, I don't know if we still use them. Camphor balls, and you place it in your drawer to smell up your clothes. Yes, right? When that camphor ball changes, it goes directly into this phase without becoming a liquid. And so it can help to keep your drawers or your clothes smelling clean. Now again, we could reverse this process and go from a gas directly to a solid, and that process is called deposition. So here we can see that the states of matter are connected. And to move from one state to the next, we would simply have to add more heat, which is really adding more energy. Heat is a form of energy. We're given the molecules or the particles in that particular state more energy to move, and as we showed earlier, once they have more energy to move, they will change from one state to the next. Okay, I hope that was clear. So as I mentioned before, everyday application of this would be, for instance, in the food industry, where dry ice is used to keep meat products and other dairy products to prevent them from spoiling, and also to keep the foods cold. Quick check. Let us see what you can do in this lesson. Why do particles move when they're heated? I want you to try to answer that question. And how or why is osmosis called a special type of diffusion? So as we close this session, let us review the key terms that were mentioned earlier. Matter is anything that has mass and occupies space. Diffusion refers to the movement of particles from an area of high concentration to an area of low concentration until it is evenly distributed. Osmosis is the movement of water molecules, and here we talk about water molecules only, from an area of low concentration of solute to an area of high concentration. And I did not mention this earlier. This happens when the water moves through a semi-permeable membrane. You can look up what that means later on. And change of state refers to how matter changes. So that's it for CSEC Chemistry. Up next, CSEC English Language. Stay with us.